This video is part of the MCAT chemistry video course. Subscribe if you'd like notifications about the release of new videos, and please visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we're going to cover how to draw Lewis structures and then how to assign formal charge from those Lewis structures. Before we get started doing Lewis structures, you want to make sure that you are really comfortable finding the number of valence electrons for an atom, and you can look at one of the previous videos on how to do that. So make sure that you have a periodic table pulled up so that you can follow along and find the number of valence electrons for each one of the atoms that we're working with. And we're going to follow a step-by-step process to draw these Lewis structures. And I'm sure a lot of you are probably pretty comfortable with drawing these without a step-by-step process. I would still just go over this so that way you have this process in your back pocket in case you come across a molecule that's really giving you trouble. So starting with counting the valence electrons for CO2, carbon has 4, oxygen has 6, and then the other oxygen also has 6. So we have a total of 16 valence electrons. Now to count the number of electrons that we would need to give each atom an octet, all we do is multiply the number of atoms by 8. So we just do 8 times 3 because we have 3 atoms, each one gets an octet, that'd be 8 electrons each, so that gives us a total of 24 electrons needed. And then we take 24 electrons needed minus 16 electrons, because 16 electrons is basically like the electrons that we have to work with. So we do 24 minus 16, and that gives us a total of 8 electrons. And this would be the amount of electrons that need to be shared. So in order for all of our atoms to get an octet, 8 electrons have to be shared. And shared electrons by definition would be in the form of a bond. So you do 8, and there are 2 electrons per bond. So you do 8 electrons divided by 2 gives you 4 bonds because there are 2 electrons per bond. So after you do this calculation, now all you have to do is finish by drawing the atom, or by drawing the molecule. So start by finding your least abundant atom. So there's 1 carbon and 2 oxygens. So carbon is the least abundant. So we place carbon in the center and then place the rest of the atoms just around your central atom. Now you just place however many bonds you calculated. So we calculated 4 bonds, and it makes the most sense to just do 2 bonds on either side of the carbon, 2 going to each oxygen. After you place your 4 bonds, count and see which atoms have an octet and which ones don't. So to figure out which atoms have an octet, you need to count 2 electrons per bond, and so each bond has 2 electrons, and those 2 electrons count for both atoms that they're touching. So if we look at this bond, for example, there are 2 electrons in that bond, and those 2 electrons count for the oxygen on the left, and they count for the carbon. So now let's see how many electrons all of our atoms have. So the carbon has 4 bonds on it, so it actually has an octet, so, because there's 2 electrons per bond. And then the oxygens, each oxygen has 2 bonds each, so the oxygens would have 4 electrons each, because the bonds are 2 electrons. So our oxygens, each of those need 4 more electrons, which we give to them by giving them lone pairs. So you write your electrons as pairs of electrons, and each one would need 4 total electrons or 2 lone pairs in order to reach the octet. And you can never place just a single electron. They always have to be in pairs, and that's because single electrons are just so reactive that it's just not realistic to place one because it would only exist for like such a short amount of time. So lone pairs are really the only things that we ever actually find. So now each atom does have an octet, and the last thing you need to do is just count your total electrons that we placed and make sure that equals the number of valence electrons that you calculated in the beginning. So we have 4 bonds total. Those 4 bonds would be 8 electrons, and then we have 4 lone pairs, which is also 8 electrons. So we used up a total of 16 electrons, which that is all the electrons we had to work with to start. All the atoms have an octet. We used up the right number of valence electrons, so you can be pretty sure that you're totally good on this molecule, that you did it correctly. Now we'll do the next one, and we'll just do the exact same process. So first the valence electrons, we have 1 plus 1 plus 1 for the 3 hydrogens, plus 5 for that nitrogen to give us a total of 8 valence electrons. The electrons that we need for each atom to get its octet would be 8 for nitrogen, and then hydrogen actually never gets an octet. The most electrons hydrogen can have is 2. So we do 8 plus 2 plus 2 plus 2, and that's the only exception. Hydrogen is the only time that you're not going to use 8 in that calculation. So we need a total of 14 electrons. Now we do our 14 electrons minus 8 valence electrons, which is going to give us a total of 6 shared electrons. And then 6 divided by 2 gives us a total of 3 bonds. And then now we just draw the molecule. Nitrogen is our least abundant atom, and then draw the hydrogens around it. We have 3 bonds, so it makes perfect sense that we'd have 1 bond going to each hydrogen. Hydrogen only needs 2 electrons, so each one of those bonds satisfies the hydrogen's need for electrons. So the hydrogens won't get any lone pairs. Nitrogen has 3 bonds on it, so it has 6 electrons, so we just need to add 1 more lone pair to nitrogen to give it the octet. Now we add up the amount of electrons that we used. We have 3 bonds, so that's 6 electrons in those bonds. We have 1 lone pair, so that's 2 electrons, which gives us a total of 8 electrons that are in our drawing, and then that does match the number of valence electrons that we counted at the beginning. Assigning formal charge may be something you're really comfortable with without a set of rules, which is totally fine, but if you have the set of rules, it'll still be really helpful in case you run across a tricky molecule. So first thing you want to do is pick the atom that you're wanting to find what the formal charge is. So for NH3, let's just pick one of the hydrogens and then follow our set of rules here. So first thing we want to do is the number of valence electrons for hydrogen is just 1. So we have 1 valence electron for hydrogen. Now we subtract the number of bonds that the hydrogen has, which is 1 minus 1. And then we subtract the number of electrons that are in the lone pairs that are on the hydrogen. And none of the hydrogens have a lone pair, so we have 0 for that one. So 1 minus 1 minus 0 gives us a total of 0. So there's no formal charges on those hydrogens. Now let's do one for nitrogen. So nitrogen has 5 valence electrons. This nitrogen has 3 bonds. And then this nitrogen has 2 lone pair electrons. So notice that we're not counting how many lone pairs does it have. We're counting how many electrons does it have that are in lone pairs. So it's a total of 2 electrons in those lone pairs. So 5 minus 3 minus 2 equals 0. So the nitrogen also does not have any charge. If we do the molecule on the right, the hydrogens would have the same thing. It'd be 1 minus 1 because they have 1 bond and no lone pairs. But if we did the nitrogen for the one on the right, we'd have 5 minus 4 because there are 4 bonds. And now we have no lone pairs. So it'd be 5 minus 4 minus 0 to equal 1. So then a plus 1 formal charge would be assigned to the nitrogen. And so that's why you see NH4 written with a positive charge. And anytime you have one of these polyatomic ions, like maybe SO4 2-, those charges, the plus or the 2-, those come from formal charge assigning. So then these formal charges actually allow the molecule to participate in ionic bonds. And that comes up a lot with proteins, which we'll see when we do this carboxylate ion on the bottom left here. You will hear about proteins having ionic interactions, and it's because of formal charges that often show up on NH4 molecules and then O- molecules, which we'll do right now. For the molecule on the bottom left, let's first start with that top oxygen. So we're just gonna do the 2 oxygens and not really worry about the rest of the atoms. So the top oxygen, we're gonna follow the same process. 6 valence electrons for oxygen. There are 2 bonds, and then we count the number of electrons that are in those 2 lone pairs. So it's 4 total electrons, gives us a formal charge of 0. Now let's do the other oxygen, the one with the other lone pairs. So that oxygen would start with 6 valence electrons again, minus 1 for the 1 bond, and then minus 6 for the total electrons that are in those 3 lone pairs, gives us a total of -1. So that oxygen gets that negative sign. And that's what we were talking about just a second ago. A lot of times you're going to see oxygens with 3 lone pairs participating in ionic bonds, especially like in protein folding or ionic interactions. And I would strongly suggest that you memorize, I'll just draw these in a box over here, that you memorize that NH3 or just a nitrogen with 3 bonds. So sometimes you'll see this written as like in R3, where those R's can be any type of elements. So those are not going to have any formal charge. Where if we have something like NH4, that is going to have a positive charge. or maybe you have NR4, and those are other groups, and so that's going to have a positive charge. And then the oxygens are the other thing that you're going to want to have memorized. Anytime that you have an oxygen with 3 lone pairs, like what we have right there, anytime you have an oxygen with 3 lone pairs, you're going to have a negative charge. Versus the oxygen, the other oxygen here, anytime you have an oxygen with a double bond, or that just has 2 bonds, it doesn't have to be a double bond. So any oxygen with 2 bonds is not going to have any formal charge. It'll have a 0 formal charge. And this becomes even more important when you start talking about protonation and deprotonation of certain acids and bases, and getting a good understanding of how pH levels and different things can affect the solubility and the types of interactions that can occur with molecules, because it affects the formal charges that they have, and it all comes back to this calculation that we did. And all that stuff will be covered in future videos, so don't worry too much about it, but it's really good practice to try to connect it to those future topics.